Below is the graph of the derivative of a function f, whose domain is the set of all real numbers, and it is continuous everywhere. Use the provided information to create a sketch of the original function if the only zeros of f are x equals -3.5, x equals 0, x equals 6, and x equals 9.5. Well, the first step in graphing this function is to actually graph out the zeros that we are provided and plot those as points. So this is where our original function f crosses the x-axis. So at -3.5, we are right about here. That's one point of intersection. X equals 0 is another. X equals 6 is another point of intersection, and x equals 9.5 is the final point of intersection. And the next step in this process is to take our graph f prime of x and use it to construct our graph. Some may elect to use sign charts as well. I'm going to. So first I'm going to make a sign chart for f prime of x based on this graph. And we know that the critical values or zeros of f prime of x are going to be -2, +3, and +8. So these are going to be the relative extrema in our regular function here. And we can tell by reading the graph of f prime of x that it is positive from -infinity to -2. That means that regular f of x will be increasing. And then f prime of x, or the derivative, is negative between -2 and +3. So that means our original f function will decrease within this interval. And then from 3 to 8, f prime of x is positive again, meaning that f of x will increase again. And then to the right of 8, our derivative is negative, which means the regular function will decrease again. Now what we can also do is we can make a sign chart for the second derivative. So our second derivative, or f double prime of x, will have critical values where horizontal tangents exist in f prime of x. So if we look at it, the derivative of f prime of x will be equal to 0 when f prime of x has horizontal tangents. And they are occurring when x equals 0 and x equals 6. And we can see then that to the left of x equals 0 in our derivative, the slope of our tangent lines here, or the derivative of f prime of x, which would give us f double prime of x, will be negative. This will tell us that the original function f of x will be concave down within this region. And then if we look at the horizontal tangents, or the derivative of f prime of x again, from 0 to 6, they will all have a positive orientation. So therefore, our function will be concave up when we graph it from 0 to 6. And then for derivative values, for x values greater than 6, within our derivative, we can see that those horizontal tangents, or the slope of those horizontal tangents, will be negative again. This means that we will transition to being concave down again at x equals 6. All right, so let's use these bits of information in order to draw a rough sketch of our function f of x. So we know that from -infinity to -2, we are increasing and concave down. So we are increasing and concave down all the way up until we get to -2. So that means we're going to cross over or cross through the x-axis. So we get about here. And then from -2 to 0, we are decreasing and concave down. But then once we get to 0, we are still decreasing, but now we are concave up. And we're going to take that until 3. So at 3, we're going to increase and still be concave up. And when we get to 6, we're going to transition to being concave down and still increasing. And then when we get to 8, we are going to increase up to 8. We are concave down, so notice how this has that curve in that direction. And then we are still concave down, but now from 8, we are decreasing again. So this looks to be a rough sketch of our function f. Let's see how accurate we were. That's actually not bad if you compare this graph to that one.